from Earth. The Webb telescope is about to unleash a new dawn of discovery. The Webb telescope separates from the launcher's second stage. The white ring close to the Earth represents the Hubble Space Telescope's orbit, and the larger orbit is the geosynchronous orbit where most telecommunications satellites are located. The solar array is Webb's first deployment. When completed, all of Webb's electrical power needs are satisfied by the solar array for the remainder of the mission. The onboard control system continually monitors and updates the attitude to ensure power generation and thermal safety. To preserve the cleanliness of the mirrors, thrusters are located only on the sunlit side of the observatory. The trajectory is designed without employing a retrofire, which necessitates pointing the delicate telescope at the sun. If course corrections are needed, these velocity additions must be done early in the flight to most efficiently use the mission's limited precious fuel. After completing mid-course corrections, the Webb telescope passes the orbit of the Moon. Webb's initial transformation is the deployment of the sunshield pallets. The tower separating the telescope and instruments from the spacecraft and sunshield is next. Next, the aft flap deploys. This is key to managing momentum buildup and fuel consumption. This structure helps to balance the pressure from the sun's light on the Webb telescope around its center of mass. After the sunshield pallets reach their final positions, the membrane launch restraints are released. These have kept the sunshield membrane safely in place from final stowage at the Northrop Grumman facility in California through shipment and launch. The sunshield protective covers roll back, permitting membrane deployment. The covers over the core region release next. Then the mid-booms extend and the sun-sized shape. It is now time to tension the sunshield membranes, each thinner than a human hair, pulling each of the uniquely sized and shaped layers to their optimal position. When deployed, the sunshield allows the telescope to cool to 385 degrees Fahrenheit below zero, cold enough to liquefy air, while the layer closest to the sun is almost 190 degrees Fahrenheit above zero, nearly the boiling point of water. It's of almost 600 degrees. Truly fire and ice. Once in the shadow of the deployed sunshield, the telescope and instruments continue cooling down to their final operational cryogenic temperatures. At the completion of membrane tensioning, the secondary mirror deploys into position and is latched rigidly in place. The aft deployable radiator releases and springs into position, allowing the instruments to radiate their waste heat directly into space and away from the telescope. Disposing of excess heat is crucial to the mission, so that it does not overwhelm the faint infrared signals to be collected from the cosmos. The cord-fold wings deploy and latch in place, completing the major deployments of the largest telescope in space. As the Webb telescope continues out to its operational orbit around the Sun-Earth L2, the observatory continues to cool down to its final cryogenic temperature state. A trajectory correction applied 29 days after launch puts the Webb telescope into its halo orbit, a key part of the mission design. The Sun-Earth L2 point is where Webb's orbit around the Sun is synchronized with Earth's. At this point, 1 million miles from Earth, Webb is free from the thermal influences of the Earth and all eclipses. Additionally, the Sun, Earth, and Moon, the brightest objects in the sky, are hidden by the deployed sun shield, giving Webb a dark, cold, and stable environment to carry out its mission of discovery. Once the mirrors and detectors are sufficiently cold, the wavefront sensing and control operations can begin. This sophisticated multi-step operation's ultimate goal is to position each of the Webb telescope's movable mirrors into their correct final positions and orientations. Once the mirrors are aligned, the mission team will continue checking out the science instruments, preparing them for operations. Commissioning is completed about 160 days after launch, and the science mission is ready to begin. This brings to fruition the work of the thousands of members of the Webb team from the United States of America, Canada, and Europe. Astronomers from all over the world can now use this facility to study the universe. NASA's James Webb Space Telescope is a game changer. Discoveries made by this observatory will rewrite textbooks, inspiring the next generation of future engineers and scientists. This revolutionary tool will provide an unprecedented view into the birth of the first stars and galaxies, unleashing a new dawn of discovery.
We have uncovered wonders undreamt by our ancestors who first speculated on the nature of those wandering lights in the night sky. We've crossed the solar system and sent ships to the stars. But we continue to search. We can't help it. A central element of the human future lies far beyond the Earth. If we crave some cosmic purpose, then let us find ourselves a worthy goal.
in the heat of the summer, these visors really can make a difference. And the Webb telescope uses the same principle to block the heat of the sun and even what bounces off the Earth and the moon. And just like my car's visor, the telescope's sunshield unfolds, but its 5 layers are a little bit thinner. This thin material is called kapton, and it makes the sunshield of NASA's James Webb Space Telescope. So what is this strange kapton? It's a combination of carbon, nitrogen, oxygen, and hydrogen, but its primary element is carbon. It is only 1/1000th of an inch thick. That's a quarter of the thickness of the thinnest hair you can find. The 5 layers of this reflective material will keep Webb cool. It'll block the light of the Earth and Moon and our very bright sun. Each layer is the size of a tennis court. The sunshield happens to be one of the most complicated parts of this telescope. And that's because it has to be packed perfectly like a parachute to fit into the rocket, and then it has to unfold in space. Let's get a better idea of how good this kapton is at reflecting heat. I asked our resident expert in all things MIDI to make me a 3-layered model of the sunshield using the same kapton that's on Webb. And then we put this tiny light bulb to mimic the heat source that would be the sun, Earth, or moon. See? You can see the heat reflecting off the bottom layer. And then the kapton worked so well that none of the heat is detected at the top of the model. The sunshield is capable of dissipating 500 degrees Fahrenheit over the 5 layers, and that heat radiates out from each of the layers. That's why each layer gets a little smaller from the bottom to the top. NASA actually uses kapton for most of its missions. It not only shields or contains heat, it also because it is electrically conductive. All that shifting kapton of the unfolding sunshield, it could create static electricity. But that charge won't build up on the kapton and jump to the observatory's super sensitive electronics. And then kapton stability over a wide range of temperatures is why it's also a great choice. This modified version, called Mylar, might even help you if you get cold.
This is your telescope, an engineering marvel, an exploration powerhouse. Use it to look back in time and explore the first galaxies that formed after the Big Bang. To peer into atmospheres of planets orbiting the stars. It's your eyepiece to the uncharted, unknown, and unimagined. This is the largest, most complex, and challenging space telescope ever constructed. It will change our understanding of the universe and our place in it. The James Webb Space Telescope. Equipped with the largest primary mirror ever to be flown in space, at 6.5 meters, it's more than 6 times the size of the Hubble Space Telescope primary mirror. Webb's 4 cutting-edge infrared instruments and cameras operate at super cold temperatures. Temperatures colder than the surface of Pluto. Getting this cold is done with the help of the largest sunshield ever flown. A 5-layer, tennis court-sized sunshield that blocks heat from the sun, Earth, and moon. Webb will be the first telescope to detect light from the most distant galaxies in the universe. These first galaxies formed about 13.5 billion years ago, only 300 or so million years after the Big Bang. Webb carries advanced technologies to tackle some of the most fundamental questions about the universe. How did the first galaxies form and evolve? Are there chemical signatures of the building blocks of life on other worlds? Is our solar system unique? Launching such a large telescope into space is an incredible engineering challenge. Fully deployed, Webb is too large to fit inside any rocket fairing. Engineers designed it to be folded, like origami, to squeeze inside the European Space Agency's 5-meter diameter Ariane 5 rocket fairing. After launch, controllers on the ground deploy Webb remotely. Deployment is an intricate ballet. For nearly 3 weeks, controllers carefully unfold Webb. After this delicate dance, Webb's golden mirrors are precisely aligned using motors behind each hexagonal mirror segment, adjusting them to form one perfect mirror. Once the instruments are fully cooled, the exploration will begin. Webb is a technological challenge like no other, born of the efforts of thousands of people across the United States, Canada, and Europe. The James Webb Space Telescope is your telescope. Use it to explore, to challenge theories, to see sights yet unseen. It's yours to unfold the beauty and mystery in the universe and our place in it.
The James Webb Space Telescope is the next premier space observatory. It will extend the discoveries of the Hubble Space Telescope and observe the birthplaces of planets, stars, and galaxies. It is named after James Webb, NASA's second administrator and champion of many NASA science missions. At 3 stories high and the size of a tennis court, this will be the largest telescope ever sent into space, and 100 times more powerful than Hubble. It is so big it has to fold to fit into the rocket only 5.5 meters wide, and unfold segment by segment once in space. Webb's mirrors are coated with a super thin layer of gold that is about 1,000 atoms thick to optimize their reflectivity in the infrared. Webb will launch from French Guiana. It is launched near the equator, taking advantage of Earth's greater rotation speed there to boost launch performance. Webb will orbit the Sun 1 million miles from Earth at the second Sun-Earth Lagrange point. The telescope will observe infrared light with unprecedented sensitivity. It will see the first galaxies, born after the Big Bang over 13.5 billion years ago. Webb's infrared cameras are so sensitive, they must block light from the Sun, Earth, and Moon. The 5-layer sun shield is like having sunblock of SPF 1 million. Webb is an international mission, with contributions from the European Space Agency and Canadian Space Agency. Scientists all over the world will be able to use Webb to explore further into space and back into time.
Hi, I'm Ellen Stofan, also known as Dr. E.
And I'm Thomas Serboken, also known as Dr. Z.
And welcome to another episode of Easy Science. We're here at the Smithsonian's National Air and Space Museum, standing in front of the backup mirror to the Hubble Space Telescope. But we're not here really to talk about Hubble. There's another big launch coming up.
We're talking about the launch of the James Webb Space Telescope. Many people have talked about it as the next Hubble, because Hubble has been transformative in our understanding of the sky.
And it's fun to be here in front of the backup mirror for Hubble. And so for people who are wondering, why doesn't this thing actually look like a mirror? It's the backup mirror. It's 2 plates of glass that are about 1 inch thick with that supporting structure in between. And if it had launched, it would have been coated in a reflective material, so it would have looked more like a mirror. These telescopes use these big mirrors to collect light, which then go into an instrument. So spectrographs are really cool instruments, and they've been used in astronomy and astrophysics for over 100 years.
Spectrographs, of course, having the ability of splitting up the light and looking at the composition of light and actually the originator, whether it's what gases is and so forth. And frankly, spectrograph also here in the museum, right?
In fact, we have over 100 years worth of spectrographs here at the Air and Space Museum. In 1929, Edwin Hubble actually used a spectrograph to determine the fact that the universe was expanding. We have a spectrograph from the Hale telescope at the Palomar Observatory in California that was used from the 1950s to the 1970s to look at the redshift of galaxies, of white dwarfs, and that helped us again understand the expansion of the universe. But I'm really fascinated with this issue of using a spectrograph to really understand what materials things are made of, how are they moving, and really just collecting that light, which James Webb will do from very early in the history of the universe.
So if you compare Hubble with Webb, there's really 2 fundamental changes. The first one is, if you look at the mirror, this is 2.4 meters. It's like this, kind of roughly kind of my height. You look at a Webb and it's unfolded, it's 6.5 meters. It's like 3 of me or more, right, with the hand up. So the other thing that's really exciting, the light that we're looking at is actually much, much colder.
And this idea that this super cold temperature and collecting this light with this big mirror is actually allowing you to look back in time as much as 100 million years after the Big Bang, which in the history of the universe, over 13 billion years, 100 million years is really soon after the Big Bang.
Recently I looked at the album of one of my children's, with all the pictures, and I imagined, suppose I didn't know about the first year, what I would miss about the story of my child. It's now in college. And I think of the universe that way. We have not seen those pictures.
Yeah, like one of the questions I've always found the craziest is this issue of black holes at the centers of galaxies. Right now, pretty much every galaxy we've looked at has a black hole at the center. And so we are really curious about these very early galaxies. Did they already have black holes? Do black holes come later? Do you start with a black hole? Like, how does that work? And that's one of the questions that JWST is really going to go after. And we're actually going to be able to use JWST to start looking at the composition of atmospheres of planets around other stars. And that's really critical in this issue of, are we alone?
Absolutely. Looking at especially cold atmospheres and kind of stars that are there, we can see molecular components, things that relate to life here on Earth, oxygen and so forth. Could you just imagine that? We're about to open that door.
And what I think people don't necessarily appreciate is the way we've had to push technology to get to this point.
Absolutely. And that's the beauty of doing amazing new